Hello. In this video, we're going to introduce you to thermochemistry, and we're going to be talking about energy and one form of energy that's heat. It's kind of a weird video. We are not going to actually apply it to chemical reactions until the third video in this series, and you really don't quite get it until we talk more about this in college chemistry too. It's a crazy system. Basically, in this video, I'm going to introduce you to a number of terms, but I'm going to give you a preview of college chemistry too. This is not just a list of names that you have to memorize for no reason other than it is in the textbook, but eventually we're going to be able to use it to determine if a chemical reaction is spontaneous or not. Okay? But like I said, you're not going to get to that point until college chemistry too. Chemical changes usually come with changes in energy, and they're very important in life. Think about when you metabolize food, when you digest food. Yes, part of it is to get materials for growth and repair, but the main purpose of food is metabolism, so you produce energy. That's called cellular respiration. You get energy out of food. When you burn fossil fuels, you're either producing heat for cooking, for warming up your house, or you're getting your car to move, so you're getting usable energy. And many raw materials, especially metals, can be purified from ores by subjecting them to very high heats. That's the example you have in there. So these energy changes are going to be very important and very common. Okay? So there's a branch of chemistry, thermochemistry, that studies the heat that's absorbed and released during chemical and some physical changes too. We did define energy in a previous video as the capacity to do work. We're going to add capacity to supply heat or to do work. Okay? As far as work, the definition they give you here is actually a physics definition, the process of causing matter to move against an opposing force. If the other day I got a package from Amazon, huge, very heavy. I had to bring it upstairs. So moving that probably 50-pound box up the stairs, it took a lot of work, right? I'm fighting against gravity. That's the force that I'm trying to move it against. Okay? There are other types of work. We'll talk a little bit in the third video about pressure volume work. Don't worry for the time being, okay? But this definition is important you keep it in mind, because when we talk about units, you're going to say some of these units are weird. Well, that's because this is one of those branches of chemistry that are so interrelated with physics that you don't know which side of the fence you're in many times, okay? We did talk previously about two types of energy. Potential energy, that's the energy that an object has because of its position. And I think I gave you an example. If I'm holding a pen, it has potential energy because if I let it go, it falls, right? Can be composition. Why does gas have energy? Well, it has energy in the carbon-carbon bonds, the gasoline, and it's potential because until you put it in the car and you burn it, you don't get the energy. And it can be just due to the condition. On the other hand, kinetic energy is the energy that an object possesses because it's moving. So we're going to review the examples we talked about then. Where that's high in elevation has potential energy, just because it's higher than where far down the river. And they give you an example here, Victoria Falls. The word on top has more energy than the word at the bottom. But when the word falls, the word is moving. The word up on top of Victoria Falls, yes, you know it's moving because the word continuously falling. But overall for Lake Victoria, it's negligible. You don't see the movement unless you're right by the falls. That's why it's mostly potential energy. But once you start coming down the falls, the world's moving. It's moving very fast. So you have kinetic energy in there. We talk also about what if you have an electron dam like Hoover Dam, where you produce electrical energy. hydroelectric dam. So the water in the dam has potential energy. The water coming down at the bottom of the dam has kinetic energy. When that kinetic energy goes to the generators, to the turbines, it produces electricity. So it produces still another type of energy. And we said then that energy can neither be created nor destroyed, but you can change it from one form to another. And we call that the law of conservation of energy. And this is just another version of the first law of thermodynamics. Okay? Every time you convert a substance into another one, there's going to be conversion of one form of energy into another, but heat is the most common one we're going to see in chemistry. Okay? If we include chemistry and physics, we may find light, electricity, nuclear energy, but we're not going to get into that right now. These next few chapters, we're mostly going to be talking about heat movement. If you remember at the beginning, we talked about the law of conservation of matter, and we said in a chemical reaction, there's no change in the total amount of matter to a chemical reaction. And now we just said there's no change in the overall amount of energy. Basically, in a chemical reaction, there is energy changes, although they're going to be small. What you're saying is basically most of the energy is going to be transformed. And of course, a lot of people figure if heat is produced, heat is lost first. Lost energy, you don't really lose it. But we're going to see energy changes, and they are little mass changes, but they're so small that we cannot measure them. So we are going to see a law of conservation of matter and the law of conservation of energy work real good for regular chemical reactions. Now, when you get into nuclear reactions, we have a problem in there because you have a very big energy change. There's mass changes that are going to be measurable. Okay, when radioactive atom decays, it loses mass. So we'll see all of that in college chemistry too. Right now, we're just going to say these are going to be different, and the matter energy conversions are going to be significant. But we'll cover that in a different video for a different semester. We're talking about heat as a common form of energy. We actually call that thermal energy. Okay? And that's the kinetic energy associated with the random movement of atoms and molecules. Okay? Temperature, on the other hand, is a measure. Is something hot or cold? Does it have a lot of kinetic energy? Very little kinetic energy. So when the atoms and molecules are moving or vibrating a lot, like in this example here on the left, they have very high kinetic energy because of the movement, and we said this object is hot. So hot temperature and high kinetic energy are related. On the other hand, when you have something that's moving very slowly, vibrating very little, it has very little kinetic energy, and we call it cold. Now, here comes two definitions that drive students crazy, and I want to get them right. Heat is not kinetic energy. Heat is the transfer of the thermal energy. Now, thermal energy is kinetic energy, but heat is the transfer of kinetic energy between two bodies that are at different temperature. If that wasn't confusing enough, some people talk about heat flow, and we are only going to mention here, and we're never going to talk about that because it's so redundant. I put it in there. If heat is the flow of thermal energy, heat flow will be the flow of the flow. Okay? But basically, the idea of heat flow is that thermal energy is transferred from one body to another. It decreases in the one that has a lot of energy, increases in the other one. Basically, you're still talking about heat, okay? That's just one term that people still use out of habit. But when do we see heat or transfer kinetic energy? When you have two objects, one is hot, one is cold, and we put them together, touching each other, some of the heat is going to be transferred from the hot to the cold. That makes sense, right? That's what happens when you put a glass of tea and add some ice to it. Heat is transferred from the tea to the ice to melt the ice, so your tea is cooler, because eventually you have the same temperature on both sides and you reach a thermal equilibrium. but please understand that heat is transfer of thermal energy or kinetic energy. Now, some reactions are going to release heat, some reactions are going to absorb heat. So, when a chemical or physical change releases heat, it's called exothermic. Exo means outside, so it means heat going to the outside. For instance, look at an acetylene torch. You're having a combustion in there that's producing enough heat to actually melt a piece of metal. Okay? If the change absorbs heat, it's called endothermic. Endo means inside, so basically it's taking heat in. And one example is those instant cold packs. If you have an injury or something like that and they give you one of those packs, basically you have an ammonium salt, there's several ones that you can use, and a little pack of water, and they tell you squeeze it. Why do you squeeze it? Because you break the bag of water and a chemical reaction takes place between ammonium nitrate and the water. It absorbs heat. So if the heat goes into the reaction, the cold pack gets cold because the heat has to transfer from one place to another. The temperature of the cold pack overall lowers, and that's how you can get an instant cold pack. Those are two terms that we're going to be using a whole lot, but like I said, it's not difficult. Exo, outside, endo, inside. Heat units, once again, it reminds me when we talk about gases and pressure and all of that, it's going to depend a whole lot on what science you're in. In chemistry, we use calories. Okay, that's the most common one. Now, no is the lowercase c. Okay, but a chemical calorie is the amount of energy required to raise 1 gram of water by 1 degree. Celsius or Kelvin, remember, they have the same magnitude. So you can memorize it one. The problem that we have also calories with the uppercase, and that is something that the food industry invented. Okay? And actually, the uppercase calorie is a kilocalorie, it's 1,000 regular calories. Why did they have to do that? I'm going to tell you the truth, it's nothing more than tricking people. If you go to a vending machine and you get yourself a candy bar, you look in the back because they give you the information they require per federal law. If you read that candy bar has maybe 200,000 calories, it's going to scare you. And, well, if you're a cheapskate like me, you'll say, okay, this is the last candy bar I buy, but I already paid for it. I'm going to eat it, but I'm never buying another one. Other people must say, I don't care that I paid for it. I'm not eating 200,000 calories, and they just throw it in the trash. So the food industry said, let's come up with a new calorie because now, if you divide by 1,000, you only have 200 calories. And most people don't realize the difference between the lowercase and the uppercase C's. So they think, oh, 200 calories, that's nothing. No big deal. I mean, it's human. 200,000 is going to look bigger than 200 any day. Even if you're aware of the trick that plays with units. And if you look at the calories in many, many food products that are prepackaged, you know what they do? So nobody can tell them they're tricking people. They write calories, all caps. So you cannot say that they're lying, that they're changing the units by using all caps. They're talking about this kind of calories, but you have no way of knowing. Okay, so this is a fake unit that the food industry uses. Okay, now the SI system uses the same units for heat, work, and energy because they're all different forms of the same, and they use the Joule. That's the amount of energy used when you use a force of 1 Newton to move an object 1 meter. That's a physics definition. I said, don't worry about it. But because some of these studies were done by chemists, some were done by physicists, when you get a problem, sometimes they're going to give you the units in calories, sometimes they're going to give them to you in joules, and you need to be able to interconvert. So 1 calorie equals 4.184 joules. And this is something that you need to find out if your instructor wants you to know that number or not. Okay? I usually tell my students I'll give it to them, but depends on the instructor. I can always, if I can find it quickly enough, give a little trick in here. Many times we promise they will give you a table of specific heats in there. You find liquid water, and now the table is in joules per gram. So that's the same number, because it uses 1 calorie per gram per degree, so 4.184. If your exam has this table and you're supposed to know the number, the number is hidden in there, okay? So that's why I tell my students, don't bother to memorize the number. But check with your instructor, he may not give you the table, he may expect you to know the number, okay? Few more definitions. Like I told you, this video is going to be mostly definitions. Heat capacity, and that's an uppercase C, is the amount of heat that the body absorbs or releases when it changes 1 degree, whether Celsius or Kelvin. Okay, so it's the total amount of heat divided by the change in temperature. Now, heat capacity doesn't tell you a whole lot because it depends on the nature of the substance and depends on the mass. For instance, when you go to the beach, you're laying on the towel, you're sunbathing, and all of a sudden you stand up on the sun and you burn your feet, right? And you have two choices. You can jump back on the towel or jump in the water. The water is always cooler. Why? Because the sun has a very low heat capacity. So the same amount of heat that only raises the temperature of the water a little bit raises the temperature of the sun a lot. It's the same amount of heat. You have the same sun shining on both of them, but the sun gets much hotter than the water, and it will burn your feet. Okay? Now, it depends on the mass too, because we are talking about, it doesn't depend on temperature and then the definition. So if you have 2 cast iron pans and you want to heat them enough to maybe cook a hamburger in there, which one will take longer to heat up? Which one will take more heat? Obviously the bigger one. It's going to take more heat. So the heat capacity of the large pan is bigger than the small one just because of the amount of iron. They both have the same material, but the masses are very, very different. So obviously people decided we don't want a unit that depends on the amount if you can help it, because once again it makes it difficult to compare results from different experiments, and they come up with specific heat capacity. Some people call it just specific heat, but that is the amount of heat necessary to raise the temperature of 1 gram 1 degree. Okay? So this eliminates the mass and is going to determine only on the nature of your material. This equation, I always tell my students, yes, you need to know it. I've told you before, I give my students many, many equations and values of constants and all that, but anytime an equation is actually the definition, specific heat, and that's lowercase, is the heat divided by the mass, so it's per gram, divided by changing temperatures by degree. Okay? This is then an intensive property, does not depend on the amount of mass, only on the identity. So back to our 2 frying pans, the specific heat is the same because they both are cast iron. We said that the last one had a larger heat capacity, but when you look at the specific heat, it's the same because they both are made of the same material. So obviously this is not going to, you don't need to know it. These numbers are given when you're having an exam in there, but you have a list of substances, you have the specific heats at 25 degrees, and notice one thing. Now, some instructors are nice, and they will give you only the specific heat of the substance that's in your problem. I like to give my students the table. Usually attach at the end of an exam a periodic table and any tables I want to give them. On purpose. Because I always want them in class, be very, very careful. The state of the matter makes a difference. Look at when you have liquid water, you have solid water, that's ice, and obviously that couldn't be measured at 25 degrees, so the one in there, that's different. And we should have water vapor. It's water. but the numbers are very different depending on the state of the matter. Okay, so whenever you're doing that, you always need to look in your problem and say, okay, am I talking about liquid water? Am I talking about ice? Am I talking about steam? And make sure you put the right number in the right place. Okay? For most of the substances you're going to be dealing with, you're only going to have in one state, but be very, very careful because water in a chemical reaction maybe produces liquid water or it maybe produces vapor. So when you're doing calculations, make sure you look at the equation, okay? Read very, very carefully. So how to calculate the amount of heat? Well, we had that equation where we set the specific heat. Remember, I told you you need to know that equation because it's the definition, divide by the mass times the change in temperature. So basically what we're doing is isolate heat. And what is the change in temperature? It's going to be the final temperature minus the initial temperature. Let me warn you, final minus initial. What if it doesn't make? Well, if you switch them, then the absolute value is going to be the same, but one's going to be positive, one's going to be negative. That is one of the major problems that we have dealing with heat with chemistry students. If you don't put this in order, your amount of heat is going to be positive or negative, and that may not be necessarily right, because we're going to see when the substance heats up, gains thermal energy, the final temperature is higher, so the value of Q is positive. When a substance loses, that means that the final temperature is lower than the initial, and Q is negative. When people are not careful to put final minus initial, you may have a case where you're actually gaining heat, but in your calculation you come up with a negative number because you reverse the order. So please, you'll save yourself a lot of trouble remembering to put this in the right order. Final minus initial, just embed that in your brain. Because in the next video, we're going to be doing calorimetry, and people come up with really weird results like, oh, the mass of, maybe I just put the hot melon in a certain amount of water, and you're calculating the mass of the melon, and come up with a negative number. No, you cannot have a negative mass. I mean, you have a piece of metal that you can hold in your fingers, it cannot be negative. What happened? Way back to the calculations, you put the temperature reverse, and then all of your signs are going to be wrong. I'm going to be as far as telling you, if it's a reaction that should have a positive value and you give it negative, or it should be negative and you give it positive, I've been counting it wrong. And always, 100% of the time, the problem comes in here. So please, please, please be very, very careful. And make sense. Let me give you an example. You get a promotion at work and you get a raise. How much is your raise? It's your new salary minus your original salary. It's positive, a raise. Right? If you reverse it, you have a negative raise. That doesn't make any sense. Okay? So please do the same thing with temperature. Change is always the final minus the initial. If you do that, it's still a good idea to keep an eye and make sure all your signs are correct, but you shouldn't have any problems. If you get that wrong, you're going to have all your signs wrong, things are not going to make any sense. And if you get me in a good day, I'm going to say, well, you did part of the calculations right. Let me see how much partial credit I can give you, but you're not going to get the full credit only because of the one mistake that I have warned you over and over and over. Okay? So here you have an example. You have 800 grams of water. The temperature changes from 21 to 85. So how much heat did the water absorb? So heat is the specific heat times the mass times the change in temperature. Obviously, you have to get this number from the table. So you get it from the table. And in this particular case, we use joules. You could have used calories. Okay. And then your answer will be in calories. Since they're asking you how much heat, either one will be correct. Okay. But many times the question will tell you how much heat in joules, how much heat in calories. So be careful. When they don't specify the unit, either one of them will be correct. But if the question specifically wants it in a certain unit, then you have to use that particular unit. But since your table is in joules per grams per degree Celsius that I will show you, we are going to use this value for the specific heat. That's the mass. Final temperature, 85, minus 21, that's initial temperature. Notice that the degrees Celsius cancel, the grams cancel, so give you the units in joules. This is an exact number by definition, so you have two significant figures, your answer is going to have two significant figures. When you put the temperatures right, final minus initial, you come up with a positive number. Yes, it's a positive number because you're adding heat. If you reverse this order because you didn't listen to me, you're going to have a negative number, meaning that you're losing heat. But you're not losing heat because the temperature went up. Okay? That's why I said it's very important that you keep up with the signs, because positive and negative means different things. But if you put final temperature minus initial temperature, you always come up with the right sign. And you don't need to worry. You may want to go back over it and say, yeah, I'll double check. But it should be okay. Now, chemists and physicists also talk about internal energy. And we're not going to spend a whole lot of time, at least not in this video. Once in college chemistry too, we talk a little more about that. But the substance can be a reservoir of energy. You can add energy to it, you can remove energy from it, and there's more forms of energy than just potential, kinetic, and all of that. So all of the possible forms of energy present in a substance, that's what we call the internal energy, and use the most common representation. Okay? One term that's very important because it's going to come up every so often. Internal energy is a state function. And a state function means that the value of it depends only on the state the system is in, not on how you reach that state. And to give you an example, Mount Kilimanjaro. You may be a mountain climber and you're going to go straight away up almost a perpendicular face in some places and all that. It's a short pathway, it's relatively short, obviously, but very steep. There is actually a dirt road that you can go around. It's much longer, but it's less steep. So some people choose one path over the other. The point I'm trying to make is that it doesn't matter which path you take, the altitude is almost 6,000 meters, it doesn't change. The height of the mountain is independent on how you get to the top of the mountain. That's an example of a state function. Okay? And we're going to be talking every so often about this particular property is a state function, this one is not a state function. That's what it means. So, how is energy exchange between the system and the surroundings? The system can be a physical thing that's changing temperature, like you put a piece of metal that's hot in a beaker of cold water, or it can be a chemical reaction and the surrounding will be all of the liquid that's left in the test tube. But change of energy take place either by changing heat or with work. Okay, so this is again repeating the first law of thermodynamics. You can change energy because you're talking about heat, work, you can convert one to another, but you don't create or destroy. Now keep in mind, heat and work are not state functions because the value depends on how you get the process. This is very generic, like I said, when we apply to specific examples, it will become clearer. But you can put energy into the system that increases the internal energy, so that's positive. How do you do that? You can heat up. Mind you have a beaker and you heat it up, you're adding heat to the beaker, so the system in there has a positive heat. Or you could do some work on it. You could increase the pressure into the beaker. Not like in a chemistry lab because you have open containers, but if it was a closed container, you could increase the pressure, maybe just pump some compressed air or something like that. If you do some work on the system, you're increasing the work. Either way, it's going to increase the internal energy. But you can also get internal energy out of the system. So now the change in internal energy is negative, either because heat is lost to the surroundings, you leave that hot beaker long enough and it's going to cool off. The heat is going to come out from the beaker to the air surrounding it. Or maybe the system is doing work on the surroundings. Think on the piston in your car is doing a work that's causing the engine to move. Okay, so when you lose heat, you also decrease. But we're having energy, moving from the system to the surroundings, from the surroundings to the system. Altogether, systems and surrounding, the energy remains constant. Okay? I know this is a bunch of definitions, and I know it's kind of confusing. We will get to use them in other videos. But still, if you have questions, remember, in the video description, there's a link to my Wisant account. If I was you, I'd watch the 3 videos before asking for help, but you're welcome to make an appointment anytime and we'll go over this material. And like I said, don't panic. You will eventually see where we're leading. Okay, I just didn't want to make a 2-hour video.